Okay, so this is going to be a very quick kinematics equations derivation. All that's assumed is some knowledge in mechanics, algebra, as well as a little bit of calculus. So we can start by recalling our definition of average velocity, which is simply our change in position over our change in time. And similarly, the average acceleration is our change in velocity over the change in time. Okay. So if we let the time interval go to 0, in other words, if we let it get as small as possible, then we can say that that's the limit as delta t goes to 0 of the term that we want to take the limit of. So the limit as delta t goes to 0 of delta x delta t is dx dt. And dx dt is our first derivative of position with respect to time, which is just our instantaneous velocity. And if we do the same thing for acceleration, if we take that limit for this term, then we get that acceleration, the instantaneous acceleration, is dv dt. And now we can use this relationship to get our first equation. So if dv dt is a, then dv equals a dt. So dv is equal to a dt, where dt and dv are differentials, so they're very small intervals, and the only way to untie those differentials is to integrate. So we can integrate both sides from v0 to v and from 0 to t, and we get that v minus v0 is equal to at, or simply v is equal to v0 plus at, where v0, remember, is the initial velocity and v is the final velocity. Okay, so now we could substitute. Well, first of all, we have our first equation of motion, and to get our second equation, we can substitute this into this v right here. Okay. So first equation and for the second equation, if we have our instantaneous velocity as dx dt is equal to this term v0 plus at, we could do the same thing we did on the first equation, where we have dx is equal to v0 plus at times dt, and now we can integrate both sides again. It's not really working. Okay. And for our x, we integrate from x0 to some x, where x0 is the initial position, and t, once again, we go from 0 to t. Now, the left-hand side is just going to be x minus x0, and this integral we can evaluate it term by term. So we can just treat these separately since there's a plus sign in between. So we have the integral of v0 with respect to t is just t v naught in the integral of at with respect to t is 1/2 at squared. So we can just write that that equals v naught t plus 1/2 at squared and our left-hand side is simply delta x. And now we have our second equation of motion. And this is the most fundamental equation. Okay. So these are our first two equations of motion. And the third equation is commonly called the time-independent equation of motion. So that gives us a hint on how to approach the problem. So if it's time-independent, that means we don't have time in our answer in the equation. There's no time at all. So we want to set our time equal to two different things so we can equate that to one thing, eliminating our time variable. So, alright, the time independent equation. So if we remember from earlier, our instantaneous acceleration is equal to dv dt, and our instantaneous velocity is dx dt. So we have two dt's, so we could set them both equal to two different things. So on the left we have dt is equal to dv over a, and on the right we have dt is equal to dx over v. And now we can set those equal to each other. So we have dv over a is equal to dx over v. And we can cross multiply and say that v dv is equal to a dx. And now we can integrate. And from v we go to some v naught to v, and x we go from some x naught to x. Rewrite those. Close enough. Okay, the left-hand side is just going to be, simply going to be, the left-hand side is simply going to be v squared over 2, evaluated at v naught to v, and the right-hand side is simply going to equal ax, evaluated from x naught to x. I don't know if I wasn't consistent with my evaluation symbol. X naught to x, which is basically just 1/2 v squared minus v naught squared is equal to a x minus x dot. And we can just say that that this term is delta x, right? X minus x naught is just delta x. I don't know why my pen's not writing right now. But basically, we can say that 2a delta x is equal to v squared minus v naught squared. And this is our time-independent equation of motion. Our third equation of motion.